All right. Good morning. How are you? Good. Very good. So let's get started. Let me turn off the. Oops. Where is it? Okay, it's here. Okay. Okay. So next time, sorry, last time we talked about using different scales for the z variable or w variable. Um, so so I got a few questions from you asking how we calculate this A matrix if we use different scale, right? So for example, if we use the scale like this and this for Z and W, so this is different from what we used to use, right? We used to use Z equals to 1, 0, and minus 1. And we use W equals to 0, 1, 0. So if we use the new scale, so how do we calculate this? A matrix try to link the newly defined variables here and the population, the group means, right? So this represents the average genotypic value for A1, the first genotype. This is for the second, A1, A2, and this is for the A2. Okay, so now how can we calculate the A matrix uh, um, so we can link the beta, which is the average genotypic value for each genotype with the newly divided mu A and D. Please pay attention when we use different scales. So this mu should be mu star, A star, and D star, because they are not exactly the same with what we defined before, right? When we used the regular definition for Z and W. So I put another additional slides in the lecture notes. So this is uh, how we can derive this A matrix by hand. Okay, so here, this is how we define the Z and W in the original way, right? Initially, we used the standard form, but now if we use different scales for Z and W, so we still use the same linear regression model, but we use different Z and different W, so we put star there. And also this will change the scale for the mu A and D. All right. And okay, so if we let's think so this is the way we define the midpoint, the additive effects, and the dominant effect when we use the standard scale, right? So the midpoint is the average between the first genotypic value and the third genotypic value, and the additive effects is actually the difference between the first genotypic value with the midpoint, and the dominant effect is the difference between the second genotypic value and the midpoint. All right. All right. Oops. Okay, so using these three equations, we can easily rearrange this equation to get this. So how can we express, I'm sorry, if we use this, sorry, if we use the new linear regression model based on the newly defined Z variable and the W variable, so we can use this to represent the genotypic value for the first one, right? The first the genotypic value equals to the mu star plus square root of 2 multiplied by the A star minus D star because of this newly defined variables, right? Okay, there's a star here. All right. Okay, So the same thing, we use this to describe the second genotypic value and the third genotypic value using the uh, using the z and the d variable with a different scales. And then based on equation 1, 2, and 3, we can easily get the original mu midpoint equals to the new mu star minus d star, and so on. So this is how we express the original midpoint additive effects and the dominant effects using the newly defined A star and D star. Okay, and then, so this is the original A matrix, right? This is the original matrix if we use the originally defined A, D, and mu A and D, then this is the A matrix, and this is the relationship between this mu A and D and the beta 1, beta 2, and beta 3. Okay, now, so because the mu star equals to this, we can easily express this as mu is here, right? Mu is here and here. So we use this to represent the mu, and we use this to represent the d over 2. And then if you combine these two, so it's easily to derive this. And the same thing for A star and D star. So if we go back, so that's how we calculate this A matrix, right? So is that clear? Any questions? Okay, very good. Let me erase these notes so we can start from here. Okay, so last time we also talked about the type 1 and the type 2 errors. So back to our business, the type 1 error in our genetic testing is defined as like when there is not a association between this locus and the phenotype, but our test claimed an association between them. So for example, if D is equal to 0, the null hypothesis is true, but our test says D is not equal to 0. So this is obviously an error. So this type of error is type 1. Type 2 is in another way. So if there is a association between the locus and the phenotype, which means like D is not equal to 0 and the alternative hypothesis is true. However, when you collect your data and follow the procedure to make a test, and the test tell you there's no association, which is wrong. So in this case, this will be a type 2 error. Okay, so actually type 1 and the type 2 error, so we can treat them as a probability. So type 1 error is actually the probability that given the null hypothesis is true, what is the chance you're going to commit a wrong core in this situation? So that's the type 1 error. But type 2 error is another probability. Given the null hypothesis is not true, what is the chance for you to commit another error? So this is the type 2 error. And so the statistical power is actually associated with the type 2 error, which is equal to 1 minus beta type 2 error. Okay, so we mentioned this, right? So this is an easy example. So here, oops, where's my mouse? Okay, it's here. So here we try to use two t-distribution or normal distribution, T0 or TA alternative. Okay, to test if there's a difference between the control and the treatment or the pre or post, right? So so by doing this, we actually, so we can think about like two beautiful dresses here, the blue dress and the orange dress. So we just fit the data with the first dress, the blue dress, the non-dress, to see if data fits it or not. So if you have a data, so you can always calculate a statistic, for example, here, right? So you got a statistic. This is the statistic. Let's say X bar or something. And this statistic will make you, will help you to calculate the probability, like the probability density function. So this is the probability, something like this. And this probability will tell you whether your data, your test statistic fits the NAM model or not. So in this case, because this data is this statistic is too far away, too far removed from the center of the non-distribution. So the p-value should be very small. And in this case, the chance that the data fits the alternative hypothesis is much higher than that for the non-distribution. So in this case, we do not believe the non-hypothesis will be true. So we reject it and we take the alternative hypothesis. So this is the procedure, standard procedure we do for a statistical test. So remember this graph. So we are actually comparing two dresses here, right? Two distributions. One is the non-distribution and the other one is the alternative distribution. So back to our own business. So we try to test. We try to test if this locus is associated with the phenotype. So this is what we do, right? We estimate. For example, this is the additive effect. We estimate the additive effects and we calculate the variance of this estimation. So we put them into the ratio to form a Watt test, which is chi-square distributed. So this is the equation for this ratio, right? The test, the statistic is here. All right. So if non-hypothesis is true, which means there's no, so the A is equivalent to the B here, so additive effects. So if there's no effects, then this statistic will follow a central chi-square distribution with D equals to the degree of freedom. So which means like if there's no additive effects at this locus, this test statistic is gonna follow the first address, which is thin and tall dress. However, if there is a additive effects, so the test statistic should fit the short but fat dress, something like this. So the only difference between these two distribution is this, the non-centrality parameter. So this thing, so if this thing is equal to 0, so this will be the non-hypothesis, the first dress, the dress we would like to fit it on. But if this non-centrality parameter is not equal to 0, so this will pull this non-distribution towards the right end, will make the distribution look like this. So two different dresses here. So we always put the non-distribution under the test, right? So we just test statistic. For example, if you got a statistic like here, so this means like the area under the curve, under the null hypothesis, this area is small, the p-value is small, which means this data does not fit the non-distribution very well. This is the non-distribution. However, on the other way, so this actually fit this alternative hypothesis distribution very well. So if you got a statistic in this position, right? So this data will be in favor of the alternative hypothesis rather than the non-hypothesis. However, think about it. So if you got a statistic very small, in this case, this thing. So when you calculate this thing, this gives you a very small number, which means this data will fit the non-distribution very well. But yeah, it fit the alternative hypothesis. It's not that well, right? So this is the same thing. So I hope you just compare these two graphs here, the same. We're comparing two distributions here. So here, when we test our own business, the association between a locus of interest and a trait of interest. So this is what we do. Any questions?
I have
Yes.
a question about, is there any relationship between A and the non-centrality parameter, delta? Like,
You mean this and this, right?
yeah, I mean, is there any relationship between A and, yeah, this one?
Yes, of course. We're going to talk about this shortly. So here, so we're going to talk about the relationship between these two things to help you to do the power calculation.
Okay.
All right, good question. So far, any questions with this test? So, because as I mentioned, so this is the very fundamental but important thing. So I hope everyone can understand this well. But starting from the chapters 8, I think, and beyond, so we're going to go very fast, go very faster because that's the applications based on what we have learned here. So still, so at this moment, I hope to keep a very slow pace to make sure everybody can follow me. Any questions about here, the slides?
So for the non-centrality parameter, I'm not quite understand the function for the function for this parameter in the chi-square distribution.
Oh, okay, got it. You mean here, this, so
Yeah.
the chi-square usually, so if, so this, so still this comes to the point where how we can relate a what test or chi-square, let's say chi-square distribution with a z variable. So, okay, so actually chi equals to the square of the z. So if this z is a standard normal distribution, then the center should be 0, right? So this, in this case, the chi-square should be 0. Think about the normal distribution, a standard normal distribution random variable. So if you calculate a square of that thing, that is always centered by 0, right? But if you take the square, so it's a non-negative thing, so that will be something like this. So if you keep sampling standard normal distribution and calculate the square of that's standard normal distributed random variable, it will give you a distribution like this. Most of the data you are gonna around this area, right? But very few data there's a chance that you're gonna get a big number. But for most of the the numbers you sampled from a standard normal distribution, if you calculate the square of that variable, so this will be the distribution. Do you agree?
Yeah.
Okay. So this is so-called the central chi-square distribution. However, if your chi-square so is related to a let's say y. So this y is a normal distribution, but it is not centered by 0. It's let's say y equals to a normal distribution with mean equals to 10, but variance equals to 1 still. All right, so what happened? If you sample a lot of y, so and calculate the square of this y, this will gives you a distribution like this.
Okay.
Because most of the thing, so 100 here, so right?
Yeah.
Something like this. So this is the relationship between the chi-square and the normal distributed variable. However, the difference between the central and the non-central is depends on the normal distribution, whether the normal distribution is centered by 0 or not.
Okay, got it.
Good question. So yeah, so we're going to talk about this again shortly. Okay, so all right, so we covered this. So if you want to control for both errors, type 1 and type 2, so for example, this is the original test. So either you can design a better experiment with the larger effect size, which means the effect size means which means the difference between the alternative, the non-hypothesis and the alternative hypothesis. So if the difference between the non-distribution and the alternative distribution is large, so that means like it's easier for you to detect the effects, right? So yeah, if you can define a better experiment with the larger effect size, so that will help with the statistical power for the detection of the genetic effects. Or if you cannot really increase the effect size, so what you can do is to increase the sample size. So if you increase the sample size, you're gonna make the non-distribution and the alternative distribution both narrower, which means they are subject to smaller standard error, and this will help you to reduce type 1 error and the type 2 error. Is that clear? Okay. All right, so this slide shows the relationship between the z, which is normal distribution, a normal distributed random variable, and the chi-square random variable. All right, the lambda. So I just copy and paste from the website. So they use different notations here, but if you understand, so the equivalent, right? So this is the non-centrality parameters here equals to lambda on this slide. All right, so here, and so I also borrowed this graph from the website. So Dr. Google is really powerful. So you can, so nowadays, I think you guys are lucky because back to my time, so maybe I should not mention this because this will also disclose my age. Yeah, so back to my time, so when I was a student, so it's not that convenient for us to collect the information we need. But now you are lucky, so it's just type in the keywords in the Google, and then you can easily find a lot of things to help you understand the stuff. So this is your application. I think, yeah, you should do better than us, right? when you approach to my career phase, so you should, yeah, you should be doing better than me. So because right now you have better tools, better knowledge, better ways to get knowledge. All right, so this is the graph. So here, the graph just shows you the different the central or the non-central chi-square with different degree of freedom. Actually, the degree of freedom here are the same, but if there's different non-centrality parameters here. So for example, this is the central, right? But those are the non-central chi-square distribution. So if you look at the central and the non-central with lambda equals to 1, the non-centrality parameter equals to 1, they are actually very close to each other. So if you want to compare the blue one with this is the dark red one, so the power should be low, right? Because the difference between these two are very small. So if you really want to test these two distributions, so you have to use a extremely large sample to do that, right? Okay. Okay, however, if your design is by comparing the blue one with the green one, so that's much easier because these two distributions are quite different, right? Which means the effect size is quite large. So in this case, you do not need to have a large sample to increase your power. So even with a small number of the sample, you can still have enough power to detect the genetic effects. So does that make sense? Okay. All right, now, so let's talk about the relationship between those parameters in the model. Okay, so let's look at the chi-square distribution first. All right, so this is the central chi-square distribution, and looks like this. Right? And okay, so if we knew this is a central chi-square distribution, and if we knew the degree of freedom, and we also calculated the chi-square statistic, then we can calculate the exact percentile or probability for this chi-square statistic, right? So if we knew this distribution and we knew the degree of freedom, then we can calculate. So if we knew, if we calculated this chi-square statistic, then we can calculate the exact p-value, which is the area under the curve of this, right? So on the other way, if we, so the same, if we knew this is a central chi-square distribution, we knew the degree of freedom, but we do not calculate, we do not know the chi-square statistic value, but we want to find that value which is associated with the percentile, the p-value like this. So we just do the inverse calculation, we can get this critical value, right? So this is what we can do. So this is for the central chi-square. We can do the same thing for the non-central chi-square distribution as well. So the only difference is like we have another parameter, right? So if we knew this parameter, the non-centrality parameter, and if we knew the degree of freedom, and we calculated and we also knew the chi-square statistic, so we can calculate the exact p-value for that statistic, right? So now for this non-central chi-square distribution, so we have two versions of the inverse function here. Erase this one and okay, so suppose we knew the parameter here, the non-centrality and degree of freedom and the percentile. So based on the definitively defined non-central chi-square distribution, we can calculate the critical value, right? The chi-square statistic. So that's what we can do. And if so, in another situation, if we knew the degree of freedom and the chi-square value, the critical value, and we want to calculate the non-centrality parameter based on the percentile, so this is also doable, right? So this is the inverse calculation. So if we knew everything else but the non-centrality parameter, we can calculate. All right, so this is the relationship. And so in power calculation, we can do two things here. So the power calculation is very useful. Probably many of you may not have this kind of feeling right now because of your early career phase. So for me, so I'm very, very familiar with this because when you want to get some money support from national agencies, for example, like NIH, NSF, So you need to write a beautiful research proposal to convince them to give you money. So in that case, you need to present a beautifully designed experiment. So you need to show why you need this money to collect this many samples so that you can achieve the power to detect the difference or the effectiveness or the efficacy for the drug. So something like this. All right. So this is one way so in that case you need to either show, okay, with this many samples, so what is the power you can achieve, or if you want to achieve some power, let's see the power here. This is a type 2 error. So power is equal to 1 minus beta, right? So if you want to achieve this power, so what is the sample size required for your experiment? So this is the power analysis. You need to use this kind of calculation to show the reviewers that your design is a good one. And if you give money to me, so I'm gonna achieve this. So this is very important. Okay, so now, so suppose this is the non-distribution. So if there's if based on the non-distribution here, what is the cutoff? What is the critical value to achieve this significance level, right? So we can. So this is the same thing here. So based on non-distribution, we can easily find the critical value for the chi-square distribution. And so this value is important. Why? Because we use this value to calculate the power based on the alternative hypothesis, right? So the alternative hypothesis, which is based on the non-central chi-square distribution. So here you see a non-centrality parameters here. So based on this, we can easily calculate the beta area. And then with the beta, so power can be easily calculated by 1 minus beta, right? Okay, so this is one situation. Another situation is, okay, suppose we want to achieve the type 2 error like this. Power, let's say power equals to 90% the power. That means like the type 2 error beta equals to 0.1. So if we want to achieve this level of the power, so what is the required sample size we need to use? So in this way, so we start from the the alternative distribution. So oops, sorry, not here, this one. So we can use this to help us to calculate the non-centrality parameter. And the non-centrality parameter is defined using this way. So I'm going to show you later why this is the case. All right, and so here this has been calculated already, and there's an unknown number here. So if you rearrange this equation, so this gives you the sample size calculation. So here, so the A is the real additive effects. So this is how, see, this is how we calculate the water test, right? So if this is not equal to 0, and this will gives you the non-centrality parameter, the calculation. All right, so any questions?
Can you, sorry, can you repeat the power calculation again?
You mean the power calculation, right? Okay, sure.
Thank you.
No problem. My pleasure. Okay, so power calculation, actually, there are two ways to do the power calculation. So this is the one way. this is another way. So the one way means like, given the sample size, how or what level of power we can achieve. So in this case, if you knew the power size, the sample size n, and so based on the sample size n, so you can easily calculate this thing, right? The cutoff, the critical value based on the non-hypothesis. All right. So once you calculate this value is also used for the rejection of the non-hypothesis. So this value will be used to calculate the type 2 error based on the alternative hypothesis, right?
Oh, okay.
Yeah. And okay, now, so think about this. Let me draw two distribution. This is what we learned before. Okay, this is H naught, and this is HA. Okay, so we always test H naught, right? So if you, let's see, if you, not good, so let me, that's fine. Let me redraw this, so it's not very good to see. Okay, so let's see, one and two. So in this case, so we'll actually compare the non-distribution with the alternative, H naught, HA. Okay, so suppose this is the cutoff you're gonna use. For 0.05, okay?
Okay.
This is the critical value you're gonna use to either reject the null hypothesis or accept it. So this also defined the area here, right? Based on the non-alternative hypothesis. So this gives you the beta. Is that right? So this area.
Okay.
Right? Okay, so the same value. So we need to find the first value by using the non-distribution. And this value, once it has been determined, it also determined the area here. So that's the beta.
Oh, okay.
All right, the power is defined as 1 minus beta, which is this. Let me make this area like this. So this is the power, right?
Right.
Is that clear?
Mm-hmm.
Okay. And so this is the first situation. Second situation is like, all right, given the power, so given the power, for example, the beta 1, we only allow the beta equals to 0.1, which means power equals to 0.9. So given this power, so what is the sample size we need to use to achieve this power? So, okay, all right, so given the power and the cutoff, so we can calculate the non-centrality parameters, right? And the non-centrality parameters is actually associated with the statistic we use. So it's like this. And this is the real genetic effect, the additive effect. Suppose we knew this. Only when we knew this, we can calculate this, right? Otherwise, yeah, it's not doable. So given the known additive effects and the residual error variance and the variance of the genotypic variable, the genotype variable, and the only thing we do not know is the sample size. So if you rearrange this equation, you can solve this n by using this. This is how we calculate the sample size. So don't worry, I'm going to show you an example immediately to see how in real situation we can implement this calculation to help us to do the power calculation. Because this stuff is very important. So definitely 100%, I'm going to give you questions like this in the final exam. All right.
Okay. Thank you.
Okay. All right, let's, so any other questions, Livy?
No.
No? Okay. Any other questions? Any other students? All right, let's move forward. Okay. Okay, let's see the sample size, the relationship between sample size and the heritability. Okay, so we defined heritability, right? The heritability actually, so this is the here. This is the uh, let's see. Okay, so the first equation here is the broad sense heritability. So the heritability means like from the total phenotypic variation. So the total phenotypic variation actually consists two parts. The first part is the variance, the variability due to the genetic effects, right? The second part is the variability, the variance due to the environmental fact, so which is not under control. So this is the genetic variance, and the broad sense heritability is equal to the proportion of the total phenotypic variation that is explained by the genetics. So this is how we define the heritability. And here we just, so now going to the next step. So here, because we only consider the additive effects, so this is the narrow sense heritability, right? Okay, so in this situation, the variance due to the genetics is only expressed by the additive effects, and the denominator is the variance due to the additive effects plus the random error variance, the variance due to the random error. And so if you divided the numerator and the denominator simultaneously by the sigma square, so you will get this equation here. And okay, now we knew what? Okay, let's see. All right, okay. Let me see. So, okay, got it. So from here to here, so you just rearrange this equation by treating this as a whole. And this, so you rearrange this, so you're gonna get this ratio equals to this, right? Okay. And because n equals to this is what we calculated for in the previous slide, right? So that's n equals to this. So now we can replace this ratio by this and plug this into here. Okay, then we get this. Okay, now, so look at here. So sample size, this is sample size. So when the heritability, so this actually, oops, this shows you this equation, final equation actually shows you the relationship between the sample size and the heritability. So suppose heritability increase for some traits, if we are analyzing a traits with a greater heritability, the consequence is what? It's like, so the denominator is increased and the numerator is decreased, and the whole thing will be decreased, which means if you are analyzing a trait with higher heritability, so if you want to achieve the same level of the statistical power, you need smaller sample size, right? However, if you are dealing with a trait with reduced heritability, with less heritability, then to achieve the same level of the power, you have to use a larger sample, Does that make sense?
Not the part about the level of the power. And that
Say that again. I'm sorry.
I understand the relationship and the red arrows that you've played out.
Mhm.
I understand that in the equation. However, I don't understand how that relates to the power.
Oh, the power. Okay, so this is the power, right? So using the power calculation, you can get this equation for calculating the required sample size. Is that right?
Mm-hmm.
So this sample size actually used here. So we just replace this by the heritability, right? Here we just, so this is part of the power calculation. We want to use the power calculation to check the relationship between the sample size and the trait heritability. So this slide shows this. Does that make sense?
Okay, I understand what we're doing now.
So yeah, this is actually part of the power analysis, but using the power analysis, we try to investigate another topic to see what the power calculation can tell us about the relationship between the required sample size and the traits of different level of the heritability. Okay,
But then you talked about increasing the sample size to increase the power, but then you won't be able to determine heritability.
So it's in that case. So yeah, good question. So I think yeah, to better answer your question, let's think about this. So suppose we're talking about three variables here. So if you want to talk about the relationship between variable 1 and variable 2, so it's better you fix the variable 3, right? Then it's easier for you to talk about the relationship correlation between variable 1 and 2, right?
Mm-hmm.
So you want to fix the third one. So here, so we're talking about three things. So the power, the sample size, and the heritability. So in this slide, so when we talk about the relationship between power and the sample size, so we fix the heritability. We talk about the same traits. So heritability is not relevant in this slide, on this slide. So if we are talking about a same trait, then what is the relationship between the power and the sample size? In this case, hello, can you hear me?
Yes.
Okay. So, oops. Oh. I think there's some, I cannot see my windows. Oops.
Same.
What happened? I don't know. Now I can see everybody, but let's do this again. Am I still connected?
Yes.
Yes.
Oh, okay. All right. This is strange. Like, no wonder Zoom, the stock price for Zoom is dropping. No, I'm kidding. So yes, because of the good news, like the COVID-19 vaccine, I think the Pfizer, they reported a positive result. So I think people think like Zoom is no longer useful. So the price dropped yesterday, but I think their service is getting worse now. No, I'm kidding. All right, so let's go back to here again. All right, so here on this slide, so first we're talking about three things: the power, the sample size, and the heritability. So if we want to understand, learn the relationship correlation between the power and the sample size, we're gonna fix the heritability. So that's why here we only talk about the one traits, no variability in heritability, right? Mm-hmm. So then what is the relationship between power and the sample size? So in this case, oops, where's my mouse? Okay, so increasing sample size will increase your power. Does that make sense?
Yes.
Okay, now here, so when we want to see the relationship between the sample size and heritability, we fix the power. So here we talk about if we want to achieve the same level of the power, what is the relationship between the sample size and the heritability? Does that make sense?
Yep.
Okay, so if we are talking about the same level of the power, if you increase the the heritability of the traits. You change it into a trait with better heritability, then you're gonna need less sample to achieve the same power.
Oh.
Make sense?
Mhm.
Great. Yeah, good question. So this is always true because the world is so complicated, complex, like the complex traits. So if you want to discover the relationship, the direct relationship between variable 1 and 2, you'd better put other variables under the control, right? So to make things easier. Okay, so now, so this is the comparison between the two different designs, F2 design and the backcross design, right? And okay, so this is how we calculate the non-contrality parameter, and this is how we use this to calculate the sample size, right? To achieve the same power. So here we are. Again, we're talking about the same power. We fix the power. So we just want to see what's the relationship between the sample size and the design. So here we're talking about the same traits. So the heritability is the same, and we're talking about the power the same. So the power is the same. However, if we want to compare the two designs, so the design is a variable now. So what is the relationship between the design and the required sample size? Is that clear? So here we're talking about different things. We put these two under the control, same power and same traits, heritability. If we want to compare another variable, which is the different design, so what's the relationship between the different design and the sample size? Because in F2 and backcross design, we knew the variance for the X. So this is how we define X, right? In F2, we can see 3 genotypes here, better design. But in backcross, we lost some information because in the backcross, we only see 2 genotypes. That's why the variance of the X is larger in F2 design than that in the backcross design, right? So if you relate this to this, what does that mean? That means like, since the F2 design has more information, so to achieve the same power with the same traits, we need less sample in F2 design than that in the backcross, which means like the F2 design requires half of the sample size to reach the same power as the backcross design. Does that make sense to you?
Mm-hmm.
Any questions? Good. Good. Thank you. Okay, so we have talked about the relationship between the what test and the z test, right? What test is a chi-square test. So we at the beginning of today's lecture, so we spent some time to discuss the relationship between the chi-square and the normal distribution, a normal distributed random variable. So whether the chi-square is a central or non-central chi-square distribution, this totally depends on the associated normally distributed random variable, right? If the normally distributed random variable is centered by 0, then the chi-square is a central chi-square. If the associated normally distributed random variable is not centered at 0, then that will give you a non-central distribution, a chi-square distribution. All right, so this is the same here. So since the chi-square distribution is tightly associated with the normal distribution, so we can use normal distribution to help us with the power calculation for the chi-square distribution. So this shows the power, the beta type 2 error is equal to not chi-square, right? Because in the past we use what? We use chi-square to calculate this beta. Oops. Here we use chi-square to calculate this beta. But here we use normal distribution. This big phi represented the normal distribution, the cumulative density function for the normal distribution. So here we can use this the cumulative normal density function to help us to calculate this type 2 error in chi-square distribution. And the power is the same, 1 minus beta. And the same here, so we can use normal distribution. Look at here. So this is the standard normal distribution to help us to calculate either the sample size, required sample size, based on the heritability, or we can calculate the non-centrality parameters using the normal distribution. So this graph, so I draw this, it's not beautiful. Hopefully, yeah, you don't mind. But I think this graph is very helpful for you to understand the relationship between the chi-square distribution and the normal distribution, and how we can use this association to help us calculate the power or the sample size in the chi-square distribution. Give me a second. Power is low, so I need to connect my computer with power. All right. All right, that's better. Okay, so here, so this is actually the distance. So we translate the high chi-square distribution into normal distribution. So here we're talking about non-distribution and alternative distribution as two standardized normal distribution. So the non-distribution is a standard normal distribution with which is centered by 0 and the variance equals to 1. And the alternative hypothesis is also a normal distribution, but it is not centered by 0. It's here. But the variance is equal to 1 as well. So this actually is the effective size, which is the real additive effects divided by the variance of the estimation of that effect. And this distance actually is, if we translate this distance into the normal distribution, this distance equals to this plus this. So, okay. It is not required. So this is only for your own benefit and knowledge. I will not test you this in the final, but I hope, like, if you are interested in this, so just spend some time to explore, make yourself understand this, and this will be helpful in your future career. All right, let's move on. Okay, so in the previous slides we talk about the power calculation based on the additive effects only. So, but in some situation or in some model, if we want to consider both additive and the dominant effect, so we can do that as well. So because here, so the non-centrality parameter, we can express this using this. So this difference means like the variance due to all the genetic effects. So this all genetic effects includes the additive effects plus the dominant effects. So we can decompose this variance due to the genetic effects into two components, right? The first component is associated with the additive effects. The second one is associated with the dominant effects. So in this case, the non-centrality parameter will be the sum of these two things. And that's the additive. And so for the additive model only, so we only calculate this, the non-centrality parameter due to the additive effects. But if you are analyzing a model with both additive and the dominant effects, so this will become the formula you need to use to calculate the non-centrality parameter that is associated with additive plus the dominant effects. Okay. All right, so I think, yeah, this slide becomes more interesting to you because this could be a very typical like a practice problem I can give you before your final exam. So I can give you something like this on the final exam. So that's why so it is important for you to understand what is going on behind this problem. Okay, let's look at this example 1 first. So here I will ask you to calculate the statistical power to detect a major gene. So here you need to calculate the power for detecting a major gene. So with the A equals to 5, A equals to 5, which means what? So we knew the additive effect, which is equal to 5. And we also knew this is from a F2 design, F2 population, and the sample size is known, which is 200. And now, so when we talk about the design, so we need to achieve the type 1 error equals to 0.05, which means like the significance level alpha is equal to, is set to 0.05. And we also assume that the variance for the residual error equals to 400. So given all this known information, so how do we calculate the power? So what is power? Power is W, right? We have the definition before. So power is W equals to, this W is not so omega actually, so it's not W, sorry. So we use omega here to represent the power, which is equal to 1 minus beta. So here the omega equals to 1 minus beta, which is the type 2 error. So this is very straightforward question. So first, based on the non-distribution, which is the central chi-square distribution, because we knew the percentile is like 0.95, the 0.95, right? Because we set the alpha equals to 0.05. And okay, so if we calculate the inverse calculation function, this will give you, what is this? The cutoff, the critical value for the chi-square, for the central chi-square distribution when alpha equals to 0.05, right? So this, think about this two distribution. This, I use the normal distribution for this example. So this area is 0.05, right? So this is how we can calculate this. This gives you the cutoff here. All right. Okay, now once you have this cutoff also associated with the beta, right? So this is the area of the beta, considering the alternative hypothesis. Okay. All right, so based on the alternative hypothesis, based on the alternative distribution, so using the same cutoff, so you can easily use another inverse function to calculate the non-centrality parameter, which is defined as this, because we already knew the real additive effects and the residual error variance, and also this, right? Okay. And so can anyone tell me what is this? The sigma square x?
The
And how?
variance.
I'm sorry?
Oh, the variance for the genotype variable.
Yes. So because this is F2, so that's very important because this also gives you some information, right? The F2 population. So when I say this is a F2 population, so immediately you can get this equals to 1/2, right?
Mhm.
Okay, very good, very good. All right. So now you can use this formula to calculate the non-centrality parameters. All right, so bingo, when you got this, so you're halfway done. So you almost get everything to calculate the power. So, all right, so here you use this to calculate your beta, and the power is equal to one more. So we just erase one equal sign here. So the power omega equals to 1 minus beta, which is this. So this design gives you 70% of the power, which is not too bad. So usually we hope we can achieve a test with power of more than like 85% or 90%. So that will give you a better design. So any questions about this calculation?
I have a question,
Yeah,
Professor.
go ahead.
So for the last line, where we have the F statistic, do we look at the chi-square table for the value?
Oh yeah, yeah. So this is not a F statistic. This is actually a function. So
Oh,
yeah. So if we use, so how can I say that? So you different fund, right? So here, if we use the Italian, so yeah, this is, so that's why sometimes yeah, different textbook use different style. Here, the F is not F distribution, it's the function. And we put a minus here, means like inverse function. So we are actually talking about a chi-square distribution here.
chi-square.
So yeah, let me see. So yes, you need to use the chi-square table for this problem.
Okay, to find if it's 0.2946.
That's right.
Right?
Yes.
Okay.
So good question. So this F is not F distribution, is a function.
Okay.
Yeah.
Do we just Google the table from anywhere? The chi-square table.
I can, no, don't worry. So yeah, you can Google. So you can easily find it. Or in the final, I'm gonna provide a table for you, chi-square table.
Oh, okay.
But it's okay. So you don't have to use my version because this is an open book, open source. So you can find from Google. Yeah.
Okay, got it.
Any other questions?
Can we calculate this function through R?
Yeah, of course. Sure. Yeah. So yeah, maybe next time I don't have the code ready for you, but yeah, maybe next time I can show you how we can use R. So even more convenient. So to calculate these values. Yeah. Yeah. Do whatever you can. Yeah. So this is an open book test. So just of course this is not a teamwork, so you cannot collaborate with other students in the test, but yeah, it's on your own. But you can find anything you can find, either the R or the online, anything that you can find, grab, just like a research. So right now, so yeah, when you do a research, so you have a goal to achieve the research, and to achieve that, so you can find everything available for you to achieve the research goal. Okay, any other questions?
One more.
Yeah, go ahead.
So in the first line, we have the notation, the function of 0.95 given 1, 0.
Mhm.
Where did this 1, 0 notation come out of? How is this defined?
Okay, so first, so when we calculate this, we need to use the null hypothesis, right?
Yeah.
So this is based on null hypothesis, which means this is a central. This is a central
Okay.
chi-square, right?
So
So when this is a chi-square, so when this is central, so this non-centrality parameter must be equal to 0. And we're talking about just the one the dominant the additive effects. We're testing the additive effects. So that's one parameter to test. So degree of freedom equals to 1.
okay, so A, that's df equals to 1, and then so the first one is the number of parameters, and then the second one we're describing the centrality or the central point.
That's right. Yes. So let's go back to here.
Got it.
Yeah.
That's all
So
we need to know.
the same thing here. So if we calculate the beta, so we need to based on the alternative distribution, right? And that distribution, for that distribution, the non-centrality parameter is not equal to 0. So this is associated with this.
So D in this equation is equal to number of parameters. I got it.
Yes. Okay, very good.
I have another question.
Yeah, the same slides, right?
Yes. So does the chi-square table differ for the central 0 parameter versus the non-central
So
distribution?
the chi-square table you can find from Google everywhere is only based on the central
Right.
chi-square distribution.
Okay.
So the non-central, so I'm not that sure. So usually I don't think that we can find any non-central, but yeah, but this is why I think, yeah, maybe next time I'm gonna show you how we can use R. So if you have a
Okay.
problem like this, so you need to use the non-central calculation. So I'm gonna show you how we can use R to do that
Okay, thank
next
you.
time. Yeah.
Okay, Professor.
Sure. Let me write down this. So in case I forget about this, I'm going to show you the R code for non-central. Right. Okay. Yes. So this is important. Any other questions?
No.
Okay, good. Okay, so the second example, it's another, so it's a reversed version. So in this case, so we need to find, so I will ask you to find the minimum required sample size to detect a gene that explains 3% of the phenotypic variance. So what does that mean, 3%?
The heritability.
Yes, the heritability equals to 3%, which means like this is not a very good, very nice trait to study. Maybe this trait is an important trait, but it's not that easy to study. Just for example, so some of my students are working on the rice genome. So because we try to find some genomic loci that are responsible for some important traits in rice. So in rice, there are many quantitative traits, including the yield. The yield is the most important trait for rice. So important, but it's not a very nice trait. So the heritability usually is very low. So that's why if you want to study genetics, to perform genetic study on the rice yield, so you have to design a large experiment, including a lot of samples, a lot of different lines to achieve that goal. So probably this is another example. So showing the heritability is not very nice. I guess 30% maybe. 3% is too low. So there's a typo here. All right, so that's why the heritability equals to 0.3. That's 30%. Okay. All right, sorry about this. So So I'm going to report this error typo to Dr. Xu. So probably, yeah. So he's going to revise the textbook to publish another version edition next time. All right. So 30%, which means the heritability equals to 0.3. Oh, no. So this go back to 0.03. So this is correct, but this should be 0.03. Sorry about this. My bad. Sorry about this. Okay, so because in the calculation, yeah, indeed, use the 3% here. So this is correct, but here, this should be, okay. Any questions? Sorry about the typo. All right. Okay, now here, the phenotypic, the heritability equals to 3%, and we want to achieve the power of this. And the type 1 error is 5%. So that's the normal thing we're going to use. So the 90% of the power will translate to beta equals to what? 0.1, right?
0.1.
Yes, okay. So now, based on this information, we can, first, we need to calculate this. This is the same. Actually, you don't have to calculate this because you can remember this number. That's easy. The cutoff, the critical value for the non-distribution, which is the central chi-square, if we want to use the 0.05, this value is always equals to this, 3.84. And the tricky part is here. So if we define the beta, which is equal to 0.1, so then I'm gonna show you next time how we use the chi-square to calculate the non-centrality parameters using this. So this will give you this, right? Okay, so we calculated the non-centrality parameter based on this power and this cutoff, and this is the value. Now, once you got this, it's easy, right? Because we have the formula specified here. So the required sample size equals to this. So the heritability is known, 0.3%, and the non-centrality parameter has been calculated here. So this gives you, not too bad, 340 sample. So any questions here? Good, very good. All right, so we're very good shape. So we're done with this chapter. So any questions so far before we move on? So we have like a couple of more minutes, so we can give so very briefly introduce next chapter. Okay, very good. So. Okay, so very good, very good. So now we start moving into the application of. So far, I believe every one of you have already learned a lot useful statistical tools that can help. So this is, I think this is the best course that you can learn the linkage between statistics and the genomics. So we try to introduce the very basic but useful statistical concepts that can be applied to a genetics problem. So once you learn this, so you in the future, so when you do your own scientific project research, so you can always use some of this to help you to do the research genetics. Okay, so next chapter we're gonna apply what we have learned to solve the problem that is related to the segregation analysis. So because this is easy, right? Right now this is so easy for you, yeah. Because here, so we're talking about one locus, the genotype here, and this is the phenotype. So we want to test if this locus, the genotype of this locus is associated with the variation in the phenotypic value, right? So we can use this linear model because this is the standard way we can define this these two variables z and w to describe the additive effects and the dominant effects. That's easy. So if I give you the data like this, you can easily construct this linear regression model and perform the test to tell me whether this locus is associated with the phenotype or not. But what if the genotype information is not available? Can we still test the association between this locus and the phenotype? Yes, we do. So one way we have learned, so if we have the information of the flanking markers, we can use that flanking markers to infer the genotype for this one, right? So that's one way we have learned this before. However, even if that situation is not doable, so can we still test the association between this locus with missing genotype with the phenotype? Yes, we can do the mixed model to do this. Oops. So yeah, I think this will be the last slides for today, but I'm gonna introduce this slides to you. All right. So what is the mixture model here? So this is a very useful tool in quantitative genetics. So this mixture model is super useful when the major gene detection. So for the major gene detection, when the genotype of the major gene are missing. So major gene means like this trait is not a complex trait, probably is a simple trait that is only associated with one locus. However, if the genotype of this major locus is missing, so how can we do that? So we can treat this problem as a mixture model problem. So if you look at the phenotypic distribution so here we still talk about F2 population. So if you just look at the distribution of the phenotype for the whole F2 population, it will show like this, the solid curve. So that's the mixture of 3 underlying distributions. So is that clear? That the solid curve here, oops. The solid curve here shows a mixture distribution of 3 underlying distributions. So the 3 underlying distributions are denoted by the 3 dashed curves here. So now we're very clear, right? So in the middle, so this distribution is due to the second genotype. Probably the first one is due to the first. And since we do not know their genotype information, so we put them together, and this will gives you a mixture distribution like this. So this is what we're gonna deal with in the next chapter. So I'm gonna show you another slide. So because this slide is associated with the previous slides, also shows you the mixture distribution, because this is a very famous scientist, Fisher. So he is a very famous statistician and genetist, because he has developed a lot of very useful, powerful tools to analyze genetic data. So this is a very famous example, the iris flower data, because at that time, so it is not that easy for him or for his colleagues to get the genetic data, right? What they can observe is just the phenotypic variation. So for this iris flower, so when he measured different measurements, so they use different multiple measurements. For example, the pedal length or pedal width. So by using different measurements, so they can clearly subdivide the mixture of 3 different genotypes into 3 different groups. So how did they do this? So this is the same thing. So we will do this. So without the genetic information, so can we still test the association between a potential major loci and the phenotypic variation? So this is what we're gonna learn next time. All right, so I think time is up. I'm gonna stop here. In the future, for the future chapter, so probably we're gonna become like a little bit faster. So because later on, when you read the textbook, you're gonna see all those later chapters are the applications of what we have learned so far. So I'm gonna stop here for today. Let's see. Okay, any questions for today's lecture? Do you feel comfortable with? Okay, very good. All right, if you do not have questions, we're gonna stop here. When you come up with some questions, just send me an email. So I will try to answer that question. And otherwise, have a good day and see you on Thursday. Bye-bye.